This project is sponsored by PCBWay. From concept to production, PCBWay provide cutting-edge electronic design solutions for global innovators including hardware design, software development, mechanical design, product testing, and certification. PCBWay engineering team consists of experienced engineers in electronics, embedded systems, and product development. They successfully delivered hundreds of projects across industries such as medical devices, industrial automation, consumer electronics, smart home, and IoT. Hello, the inspiration for this project comes from classical aircraft cockpit instruments used for navigation, orientation, and flight monitoring. In aviation, instruments such as the artificial horizon, magnet compass, altimeter, and altitude indicators play a crucial role by providing pilots with real-time information about the aircraft orientation, heading, and altitude. The system is built around the CrowPanel 2.1-inch HMI ESP32 Rotary display, which integrates an ESP32S3 microcontroller, a round display, Rotary encoder with push-button functionality, and expansion interfaces for external peripherals. These features make the module particularly suitable for the implementation of compact instrumentation and graphical control systems. The MPU6050 6-axis accelerometer and gyroscope module provides information about the pitch and roll orientation of the model. These measurements are processed and converted into graphical movements on the display. In addition, support for QMC 5883L magnetic compass sensor was implemented to provide heading information for the compass instrument. The first instrument implemented is the artificial horizon, also known as the altitude indicator. It displays a blue upper area representing the sky and brown lower area representing the ground. The MPU6050 sensor continuously measures the pitch and roll angles of the model, and these values are used to dynamically rotate and shift the horizon line. A fixed yellow aircraft symbol remains centered on the display, while the horizon moves relative to the aircraft, closely replacing the behavior of a real aviation altitude indicator. Additional visual elements include pitch reference marks, a horizon scale, a virtual runway representation, and a roll angle indicator located at the top of the instrument. When nose of the model is raised, the horizon moves downward on the display. Conversely, when the nose is lowered, the horizon moves upward. Rolling the model left or right causes the entire horizon to rotate accordingly. The second instrument is a graphical magnetic compass. It consists of a circular compass card displaying cardinal directions and angular markings around its circumference. A fixed aircraft symbol is positioned at the center of the display, while the compass card rotates according to heading information obtained from the magnetic field sensor. Although the current implementation serves primarily as a simulator rather than a precision navigation device, it demonstrates the integration of a digital magnetometer via I2C communication and the graphical representation of hiding information on a circular display. The third instrument is an analog-style aircraft altimeter, inspired by traditional mechanical altitude indicators. It features a circular scale and two pointers similar to those found in a clock mechanism. The simulated altitude is initialized at 6,300 feet and then dynamically changes according to the pitch angle measured by MPU6050 sensor. Raising the nose of the model gradually increases the indicated altitude, while lowering the nose decreases it. The rate of altitude change is proportional to the measured pitch angle, creating a realistic simulation of aircraft climb and descent behavior. This approach demonstrates how sensor data can be transformed into meaningful aviation-style instrument indicators without requiring an actual altitude sensor. A fourth display mode was implemented to provide a direct graphical representation of the MPU6050 measurements. This screen displays a simplified aircraft model that rotates according to the measured roll angle and moves vertically according to the pitch angle. This visualization serves both as a demonstration as a diagnostic tool, allowing easy verification of sensor operation and aircraft orientation in real time. The Rotary encoder integrated into the CrowPanel module is used for adjusting display backlight brightness through PWM control. The encoder push button allows the user to switch between the different instrument screens, transforming the device into a multifunctional avionics display. This approach provides an intuitive and practical user interface while requiring minimal external hardware. The software was developed using the Arduino framework for ESP32 S3. Graphics are rendered using the Arduino GFX library, together with a custom frame buffer implementation enabling smooth drawing of circular instruments and dynamic graphical elements. The program structure is organized around multiple display modes, each represented by a dedicated drawing functions. This modular approach simplifies future expansion and maintenance of the code. Additional instruments can easily be added by implementing new display screens and linking them to the existing menu system. Sensor acquisition, graphical rendering, user input handling, and display updates are executed in separate logical sections of the program, improving code readability and scalability. And finally, a short conclusion. The project successfully demonstrates the integration of graphical user interface, I2C sensors, and ESP32 S3 microcontroller into a compact avionics instrument simulator. This CrowPanel display provides to be an excellent platform for this type of applications thanks to its integrated circular display, Rotary encoder, processing power, and expandability through external sensors.